Hello everyone, welcome to our next lecture, that is shear stress in beams. So before starting this lecture I will discuss few points first. First point is centroid. What is centroid? So centroid is basically center of a area. Center of a area. Okay, like if there is certain reason provided, some certain reason is given, certain reason which we are considering in a given plane. Okay, then the center of that area is your assumed to be centroid, and centroid is given as centroid is written by denoted by x bar or y bar. Okay, so x bar, or I can write xi bar. Okay, so let's proceed to x bar. So x bar can be written as a1 x1 plus a2 x2 plus similarly up to an xn divided by a1 plus a2 plus up to an. Okay, and for this we have let me draw a figure here first. So let's say this is our y axis, this is our x axis. Okay, and let's say that this is our area, region of consideration, region of study. Okay, so in this region if I want to, let's say, calculate your centroid of this region, so what will I do? Like I will like consider small region, small area. So let's say this area dA, and we are having it at distance x from the y axis and distance y from the x axis, from the x axis, distance y from the x axis. Okay, let's say that the centroid of this plane lies here. So this is our centroid. So centroid, like if we want to, like if I like remove the total area and I want to like place it in a single point, so I can do it at the centroid. Okay, and let's say that centroid is at our x bar, and here it is, it is y bar. So the centroid is at x bar and y bar, and centroid is of course denoted by your capital C. Capital C is used for centroid. So your x bar is denoted by this, or we can also write x bar as integration of x dA upon integration of dA. Okay, and this centroid, first of all let me mention it here, is also known as your first moment of area. First moment of area. I won't be like entering into your derivation for this value of x bar. So you can like refer book if you want to see how the x bar and y bar are defined. This is a very simple derivation, and I can write similarly. I can write y bar is equal to a1 y1 plus a2 y2 up to an yn. Okay, and I am using like addition sign everywhere. Okay, like say if it is a figure where certain area is missing. Okay, so you can also use the same formula there also, but you instead of positive sign, if a particular reason is like removed, is not in the consideration, so you will use negative sign there. Okay, like we will also see some examples in the further discussion, and I will show you there in those examples how to write centroid for above mentioned case, for different cases. Okay, so this is your centroid, and there are two important points. So like first is your centroid C always lies on axis of symmetry. Axis of symmetry. Like if a figure have only one symmetry, axis of symmetry, so thus your centroid point will always lie on that axis of symmetry only. C lies on intersection of two or more axis of symmetry, and of course it is if present. Okay, if like there are two or more axes of symmetry present, then your C value of your centroid will lie on intersection of those axes. Okay, now I will be moving to my next topic, that is moment of inertia. Moment of inertia. Okay, so like I mentioned that your centroid was first moment of inertia, and similarly your first moment of area. Similarly, your moment of inertia is your second moment of area. Is second moment of area. Now, so I can write like Ix is equal to integration of y square dA. Okay, and Iy is equal to integration of x square dA. Okay, so this is your moment of inertia. Now if I like I can write it as Ixc and Iyc, and these are your also called your centroidal moment of inertia. Okay, or self moment of area, or self moment of area. Okay, now this moment of inertia can never be zero, always non-zero and positive. Okay, so moment of inertia is always non-zero and positive value. I hope you remember this. So now we have one important topic that we will be frequently be using in our calculation of moment of inertia, and that is parallel axis theorem. Okay, so like parallel axis theorem is used to like derive your inertia values, inertia about a particular axis, if inertia about central axis, so I mean axis passing through centroid of the figure is known. Okay, and that is also to be needed to be parallel. Okay, now let me show it in like in form of diagram. Okay, so let's say this is our coordinate system. This here is y axis and this is your x axis. Okay, let's say this is our area which we are considering. Okay, and its centroid lies somewhere here. This is our centroid. Now let's say that yc is the your xc and yc are ordinate axis passing through your center. Okay, now if we consider certain area, okay, let's say this is this x is at a distance d1. Okay, and this y is a distance d2 from yc. Okay, now in similarly here also we will consider let me draw it area. Okay, and area will be dA. Okay, now again the distance of x from your y axis and xc from your yc axis. Okay, using like in similar way as we have like I won't be doing the revision here, so I will obtain my inertia. Okay, let me write it with the ink pen. About inertia, moment of inertia about x-axis is equal to I about xc plus area into d1 square. Similarly, I about yx is equal to I about yc plus a d2 square. So these two formula, or basically this is also a single formula, okay, is a very important relation used in our study of moment of inertias. Okay, now let me describe what does this how to like write this formula. Okay, so there are certain conditions like I like xc and both x's which you have to like convert must be known. Okay, so I sorry, I mean both axes must be parallel. Okay, so first condition is parallel. Second is IXC, I mean across centroid, or if you want to like calculate across centroid, then across the given point must be known. So IXC or IX must be known. Third, A and D must be known. Okay, in that case we can calculate like in the most of the cases, what you know, for a given figure you generally know the moment of inertia values across about their centroidal axis. Okay, and in those cases what we have to do, we have to like transfer the axis. Okay, like we have to consider across a different axis, so to calculate that we use this formula. Okay, so I about unknown axis will be I about centroidal axis plus area times of distance between the axis times square. Okay, now I will be and of course there is one more theorem, let me mention it here also only. So this is parallel axis theorem. The next one is perpendicular axis theorem. Perpendicular axis theorem. Okay, so we know the value across Ix. Okay, value of Ix, Iy. Okay, let's say I want to calculate the inertia about the plane which is perpendicular about the axis which is perpendicular to the given plane. Okay, let's say about this axis, if I want to calculate your moment of inertia. Okay, so this is this axis is generally called your polar axis. Okay, so we mention it as Ip, or like we can also write it Iz. Okay, and this is called your polar moment of inertia. Okay, and Ip is given by Ix plus Iy, and can also be given as Ixc plus Iyc. Okay, so I hope you understood till here. Okay, so your polar moment of inertia is given by sum of inertia across in the plane like for two perpendicular axes. Okay, so both Ix and Iy must be your perpendicular. Okay, now I will provide you with the centroid and moment of inertia values for some standard figures which we generally used in our study. Okay, so let me draw it here first. So here are some figures that we will be using frequently in our study. So here I will mention you centroid and their moment of inertia about the given axis. Okay, now from this first it is rectangle. So area of rectangle you all know is B, like B is the width and H is the height. So B into H will be your area is equal to B into H. Okay, now if I want to calculate x bar, so x bar will be b by 2 and y bar is equal to h by 2. So area and the centroid location. Okay, now if I want to write your moment of inertia, so moment of inertia about x will be your b, like parallel to the x-axis b, and perpendicular to the x-axis, that is h. So and h cube by 12. This is our inertia about x-axis. Similarly, we can write inertia about y-axis is equal to h b cube by 12. Okay, and if I want to write the polar moment of inertia, so I can simply add both. So in that case I will obtain bh by 12 into h square plus b square. Okay, now our next figure is triangle. Okay, so in case of triangle I can write my area is equal to this is bsb is base is b and height is h. Okay, so again bh by 3 is the area. Okay, I can write x bar. So since this line is our axis of symmetry, so this should be b by 2. Okay, and y bar is given by your h by 3. 1/3 at 1/3 height there is a centroid location. Okay, okay, if I talk about moment of inertia, so moment of inertia about x-axis is given by bhq by 36. Okay, and moment of inertia about y-axis is mentioned by h b cube by 48. And of course, if I let's say I want to calculate your moment of inertia about this axis, let's say this is our bb axis, so I can simply write I about bb is equal to bhq by 12. Okay, and this is similar to your that of rectangle. Now if I want to, let's say if it is a small point, you all also know, for equilateral triangle, for equilateral triangle, what is the condition? The condition is our value height is equal to root 3 by 2 times of base. Okay, okay, now moving to your trapezoid. So let's say this is your trapezoid. So in case of trapezoid, your area, as you all know, is given by half into base I mean sum of parallel sides, that is a plus b, into height. So we generally write it as this h by 2 times of a plus b, h by 2 times of a plus b. This is our area, and this y bar is generally used. Okay, x bar is not like used in case of a trapezoid, although it is, if it is asking question, you can always calculate it. Okay, but y bar, you should remember this point, is mentioned by y bar is equal to. Okay, so there are 3 parts to this. Like, let me show how you can remember these parts. Okay, so first h by 3 will remain. Okay, so it is in form of triangle, so h by 3 will always be there. Now above there are 2 terms, above and below. Okay, below it should be a plus b. Okay, and above, like this is y bar, so the opposite side is having a length, so twice of opposite side plus corresponding side. Okay, from where you are calculating y bar, so twice of opposite plus corresponding upon sum of both side into h by 3. This is your centroid y bar. Okay, now if I want to calculate, let's say, your ix, so I can write ix is equal to h cube by 36 into a square plus b square plus 4ab divided by a plus b. Okay. Now next is our circle. If your circle is given, then for circle we know that area is given by pi r square, or we can write in terms of your diameter pi d की power 4 by sorry about that, pi d square by 4. This is our area. Okay, and we can write that moment of inertia about x will be equal to moment of about inertia about y, and this value will be equal to our pi d की power 4 upon 64, or can also be written as pi r की power 4 upon 4. Okay, so we will be using generally this formula, pi d की power 4 upon 64. Okay, and polar moment of inertia here can be written as like ix plus pi iy, so it can be written as pi d की power 4 upon 32. Okay, so in case of your circular ring, so for circular ring you can write area is equal to pi dt, or let's write diameter dt, or can be equal to 2 pi r into t. Okay, and if I want to write ix, that will be equal to iy value, and can be written as pi r cube t, or can be written as pi d cube t by 8. Okay, and if I want to write calculate polar moment of inertia, so that can be written as 2 pi r cube t, and that also equal to pi d cube t by 4. Okay, so I hope you remember these formulas, and these formulas, these moment of inertia and centroid values will be used in our further study in this chapter. Okay, so now we will start with real shear force in bending moment. So now from here we will be starting our actual chapter, that is shear stress in beams. Okay, so the shear stress in beams, we consider a few assumptions. Okay, so let me write some assumptions here. So in the first chapter I mentioned some standard assumptions of your strength of materials, that is material should be always be homogeneous and elastic. Second is the material always obeys Hooke's law. Okay, and there are many more. Now here I will be mentioning an extra assumption, and only that I will be writing here. So assumption is shear stress is assumed to be constant along width and only varies along depth. Okay, so let me draw a diagram here. So let's say that for this load, so this is our beam and load P is applied at the end of cantilever. This is our cross section area. Okay, let's say that at a certain point, let's say on this line, okay, we have to consider the shear force values at two cross sections. Let's say cross section this and cross section this. Okay, or for better, let's remove the load P, and I will apply some UDL. Let's say there is some UDL acting. So let's say that this is our UDL. Okay, so this is our x1 plane, this is our x2 plane, and let's say that dx is the distance between both planes, and this x1 is a distance, let's say x. Okay, and say let's nomenclature, I will write some letters here, A, B, C and D. Okay, now on the cross section we can say that at a distance y we have considered our region, that is AB line is at a distance y from your neutral axis, and this, let's say, is our EF, and of course EFGH, this complete bar is EFGH. Okay, and we have to like calculate what should the shear force acting on uh, this diagram. Okay, so if I say the shear force acting at point y, so it should be the summation of all the shear forces acting above that point. Okay, so this area will be the shear force acting on this area will be our solution. Let's say this is our width B of the beam. Okay, and of course here again I have drawn the section here, so or let me I can write it as x1, x2, x1, x2, and this figure indicate exactly this thing only. This is our x1 plane, this is our x2 plane, and this distance is our dx. Okay, and at a distance y from the neutral axis, this is our region, that is A, B, C and D. Okay, now there are some forces acting on this region. Okay, so what are the shear forces acting? Okay, so first is our shear force. Let's say that at this plane the shear force is S plus ds. Okay, and here the shear force, let's say, is S. Okay, let's say that bending moment is acting as, here it is our M, and here it is our M plus dm. Okay, now so for this particular element ABCD, what we can do, we can write like using the bending moment equation, we can write sigma at, if we talk about at x section. Okay, well, let me write at x1, if we talk about x1, so I can write sigma is equal to, okay, sigma is equal to m by I into y. Okay, m is the bending moment, I is the moment of inertia, of course about neutral axis we are talking about here. Okay, now if I talk about at x2 section, so our stress will be sigma plus d sigma, okay, is equal to m by, like this bending moment is also we have mentioned m plus dm. Okay, divided by I into, this is y. Okay, y is constant. Okay, here na m plus dm, and here bending moment is m. Now, so using this equation we can also write the small force which will be acting on, if we consider a strip here. Okay, let's say we have considered a strip of width dy. Okay, in that case we can write df is equal to, so stress is our force is our stress into area, that is sigma into a, sigma into area of strip, or let me write it like as I already mentioned it this in your last chapter, m by I into y into dA. Okay, and similarly here also I can write that my df can be written as, or let me write it, df is equal to m, or I can write force is equal to this here. Okay, and here I can write F plus dF is equal to m plus dm by I into y. Okay, now if I of course this is dA, the area of strip. Okay, now if I use both these equations, so I can find my change in that small force from in dx length, that is df, will be represented by dm by I into y dA. Okay, so on integrating I can calculate F is equal to integration of dA, sorry df, and this integration, and this F is our shear force. So if I say the shear force at a distance y from the beam, so this is this complete area. Okay, so the integration is from y to d by 2. Okay, so this will be equal to integration dm by I into y dA. Okay, now this dm by I is constant for a given section. Dm by I is constant, and the integration of y dA, and this y dA is from y to d by 2. Okay, now this here, this y dA and from y to dA is also like representing the moment of area, that is first moment of area about neutral axis. So distance y and area, this area we are integrating it from here to here. So like we can like indicate this complete term or replace this complete term by using centroid of this region, centroid of the shaded region. So let me write it here. So let's say this C is the centroid of this region, and let's say this is acting at distance y bar. Okay, so what I can do, I can write F is equal to dm by I into a y bar. So this is our force, that is our shear force acting on our strip, okay, of length dx. Sure. Now what we can do, let's say that tau is the shear force acting on so tau is the shear force, sorry shear stress acting along, like acting on acting on strip, and that is at a distance y from the neutral axis and having area dA. So I can write F is equal to tau into area, and now area will become B, that is width, into D. Tau is your shear stress acting along length dx. Okay, so of course we are talking about like shear stress acting on this line EF. Okay, on EF if we are talking about. Okay, so this will be your complete area, this area into tau, that is shear stress. So tau into area, that is B width, and dx is your sorry B is B of course B is depth, width, and dx is your depth. Now this will be equal to your dm by I into a y bar. Okay, so I can write tau is equal to dm by dx into a y bar upon I into B. Okay, so we know that this dm by dx is also represented by shear force. Okay, like dm by dx is equal to shear force at any section section. Okay, so I can write tau is equal to SA y bar upon I times of B. So this here is your shear stress equation in the beam, and this is very important equation. This only equation will be used in the complete chapter. Okay, now here of course let me write the terminologies here. So S is your shear stress, shear force, not stress. Okay, and A is the, or I can let me write it as A y bar. This is moment of area above y about neutral axis. Okay, y bar of course distance of centroid. Okay, I is your moment of inertia of your section. Okay, now of course B is your width, and last but not the least tau, that is shear stress. Okay, so this is our derivation for shear stress in your beam. Now we will look into some examples and some very standard shear stress distributions that are generally mentioned in the books. Okay, and are also generally asked in your examination. So let's move to first one. So first one is shear stress distribution. Shear stress distribution in rectangular sections. Okay, so if I want to calculate, let's say, shear stress distribution in our rectangular section. Okay, so we know that shear stress is represented using SA y bar upon IB. Okay, now since I have already mentioned that the beam is section is rectangular, so if I use a rectangular section, so let's say this is our rectangular section. Okay, now this, my friend, here is your neutral axis. This is your neutral axis, and above the neutral axis at a distance y. Okay, so here I will be also showing my stress distribution plot. So let me just draw it here. Okay, so here I will be showing my stress distribution plot, how the stress varies. Okay, so let's say that at a distance y from the neutral axis, I have considered an region. Okay, so like I will find the state, like the variation of stress, shear stress with y, that is your distance from neutral axis. Okay, let's say that this region having centroid at this point and is at a distance y bar from the neutral axis. Okay, therefore this is our centroid. Okay, now here let's say B is the width of your beam. Okay, and D is the depth. of the beam. Okay, so if I want to write the equation of shear stress, so I can write it as tau is equal to SA y bar upon IB, as I mentioned. Now shear stress S will remain same, and the area A will become So let me write it A. So A area will be here, will be like dimensions, product of dimension, that is width is B, and into height is our d by 2 is the half height minus y is the distance from neutral axis. So this should be our area. And if I talk about y bar, so y bar should be your d by 2. It should be like average of this dimension and this dimension. Okay, so we can write it as d by 2 plus y divided by 2. Okay, so this should be our y by 2 plus d by 4. So we have obtained value of our shear stress and area, our area and centroid. So we will substitute these values here. And of course I for rectangular section, as I mentioned earlier, is BD cube by 12. Okay. And this I will be of course about neutral axis and is of your whole complete cross section. Okay, so if we substitute the values here, so we will obtain S times of B times of d by 2 minus y into, let's write it in this form only, that is d by 2 plus y divided by 2. Okay, and this complete term will be divided by your I, that is BD cube by 12 into B. Okay, now I can write it as S. Now this B and B will be removed. Okay, so S times of, let's remove it, 12 upon B square D cube into here this term will become d by 2 square minus y square. Here we have used the property a square minus b square is equal to a plus b upon a minus b. Okay, upon 2. Now this term can be written as tau is equal to 6s upon b d cube. Here it should be only b. Okay, because we have removed substituted, obsoleted this b with using this b. Okay, now so bd cube 6s upon bd cube times of d2 by 4 minus y2. Okay, so this is our distribution of stress. Okay, on your rectangular cross section. Now from here we can see that your stress distribution is linear, parabolic. Okay, but we have to calculate the maximum value where the maximum value of the stress lies. Okay, so for tau to be max, for tau max, what we will do, we will differentiate tau with respect to y and substitute equal to 0. Okay, and from this we can say that our tau at y is equal to plus minus d by 2. If I substitute d plus minus d by 2, so this tau will become 0. Okay, I hope you understood till here. So now if I want to, let's say calculate the tau max location of tau max, so I can calculate del tau by del y. Okay, and that would be from here, so I want, okay, let me do it. Del tau by del y is equal to 6s by bd cube. This will remain same, and this term differential will become 0 minus 2y. Okay, and substituting this equal to 0, from here we will obtain y is equal to 0. Okay, so using this equation we can say that tau is maximum at neutral axis. Okay, so the curve should be if we want to draw the curve shear distribution, so at y is equal to plus minus d by 2, the stress should be 0 and will be maximum at neutral axis. So we can draw it like this. Draw it like, okay. So this will be our neutral axis, tau max, okay, and this is our stress distribution, okay. Okay, I hope you understood till this point. Okay, now for maximum value, so we can write that tau max is equal to, like, we will substitute y is equal to 0 here in this equation, and we will obtain value of tau max is equal to 3/2 times of S upon BD. Okay, if we solve this, so we will obtain this equation, and from there we can write tau max is equal. Now one more thing, we have defined here tau average term, that is average shear stress, that will be shear stress upon cross section area, and here cross section area is our S upon BD. This is our tau average. Okay, so I can mention that tau max is equal to 3/2 times of tau average. Okay, now of course we can also calculate the location at which our tau max is equal to tau average. So we can so no tau max, our tau is equal to tau average. So tau is equal to tau average is, if we substitute it here, so we will get 6s upon BD cube into D2/4 minus Y2 is equal to S upon BD. This is our tau average. So from here we can calculate the value of y to be, or let's say that this is y bar. Okay, so y bar is equal to plus minus D upon 2√3. So at this location we will obtain the value of tau is equal to tau average. Okay, so value of tau is equal to tau average at y is equal to plus minus D/2√3. Now we will be moving to our next general shear distribution that we generally study, that is of triangle. So we have already studied the shear distribution in the rectangular section. So shear stress distribution in triangle, or like triangular section. Okay, so let's consider a section that is triangular. Okay, so let me use this section here. Okay, so this section we will be considering for our study here. Okay, now I will be also drawing your neutral axis here. So let's say this is your neutral axis. Okay, this is your neutral axis, of course, and the neutral axis will be of course I have some distance from here, and here I will be showing my stress distribution. Okay, let's say that I have considered an element, or let's say I have considered distance y. Okay, sorry, let's say that at a distance y we have considered an element, and if we consider this complete region, so let's say that C is the centroid for this region. Okay, so this will be our y bar. Okay, so let's say this is this triangular section having base P and the height h. Okay, height h is such that this distance is 2h/3. Okay, and this distance is your h/3. Okay, now let's say that this distance from the top, let's say this distance is our x, okay, and this strip width at this section is bx. So this section, the strip width is bx, okay. So I can if to calculate the shear stress, we know that shear stress can be written as S A y bar upon IB, okay. Now from this figure, let's say if I want to write your y bar, so y bar can be written as of course this distance, that is y plus centroidal distance of a smaller triangle, that is our x by 3. Now there must be some relation between x, y and y, and that relation is, let me mention it here above these all, okay. So from here we can write that our x plus y is equal to 2h by 3, okay. So from here we can write that our distance x is equal to 2h by 3 minus y, okay. So if we substitute these values here, so we will obtain y plus now x by 3, so this will be 1 by 3 times of, or we can before substituting we can proceed in terms of your x only, and after the solution we can substitute the values of value of x here, okay. So like here, let me do convert this into your terms of x only. So if I want to convert in terms of x only, so for that I can write y is equal to 2 by 3 h minus x, so this will become 2 by 3 times of h minus x, okay. Now I can also write your value of area. This area is equal to half times of base, that is bx, into x, height, that is x. Now bx, we can write bx as we know that distance b, it reaches distance, if we see from top point this, so we know that it reaches distance b, width b, in distance x h, okay. So in distance x it will reach bx is equal to b by h into x times of x, okay. So area will be half times of b by h times of x square, okay. So we can write it as b x square by 2h, okay. So our shear stress can be given as S, that is remains same. Area is our bx square by 2h into y bar is 2 by 3 times of h minus x, okay, divide by our I into b. Now we know that for triangle, our moment of inertia about your centroidal axis is given by bh cube by 36 into b. So and this b will become bx, and this bx value is b by h into x, okay. Now if we solve this, so we will obtain our value of tau is equal to 12 s upon b h cube times of hx minus x square, okay. And of course this equation is also our parabolic equation, okay. So in terms for our triangular section also, the stress distribution is parabolic only. Now from here we can write at x is equal to 0 and x is equal to h. At these both conditions, there will be condition that is tau is equal to 0. So at this point and this point, from x we are measuring from top point, so x is equal to 0 here, and h, that is base, the shear stress value is 0. Now to calculate our maximum shear stress, we will use del tau by del x, so d tau by dx, and that can be substituted equal to 0. From here we will obtain our value of x is equal to h by 2. So at x is equal to h by 2, our shear stress is maximum. Okay, so so it will be something like this. Okay, so this is our tau max. Okay, and this value is our tau na. Okay, stress distribution. Okay, now if I want to calculate tau max, so I can write tau max is equal to 3 by 2 times of your s upon bh by 2. Okay, so this will be our, so let me write it in next line only. So tau max will become 3 by 2 times of tau average. So this relation is similar to that we have obtained in our rectangular section. Okay, now if I want to calculate the shear stress neutral axis, so let's say tau at neutral axis, so we will substitute value of x is equal to 2d by 3. So from there we will obtain value is equal to 8s upon 3bh. Okay, so I can write tau na is equal to 4 by 3 times of tau average. Okay, so the case for your rectangular section is almost similar to that of your triangular section. At triangular section also the maximum stress occurs at half distance, half height. Okay, but at neutral axis, the stress in your rectangular is same as that of your tau max, and but in case of triangular section, your at neutral axis your stress become 4 by 3 times of tau average. Okay, so we will moving to our next section that we generally go through in our studies, that is our circular section. So third is our shear stress distribution, shear stress distribution in circular section. Okay, so let's consider circular section. So this is our circular section. Now okay, so if I want to draw your shear stress diagram, so let me draw a few lines here. So these are our extreme lines. Okay, and this is our neutral axis. Okay, and this will be our shear stress distribution from this point. Okay, so if we consider an element that is at a distance y from the neutral axis, so let's say this is our distance y from neutral axis. Okay, and this element does have, let's say, sorry about that, this element have dimension, or let me say that the size okay, So this width of the strip is our dy. Okay, let's say this strip to be F. Okay, and the area of this strip dA area of this strip will become B, that is width of the strip, into dy, that is high depth of the strip. Okay, and of course let's say that r is the radius of your circle. Okay, so this dimension is our r. Now if I want to calculate the shear stress, so I know that shear stress is given by standard formula SAY bar upon IB. Now here we have to calculate the value of A and Y bar. Okay, so for A first we have to calculate the value of B. Okay, so for B we know that B can be provided as B is equal to, so this dimension is B. Okay, let's consider the half of this dimension, that is B by 2. So let me draw it here. Okay, so this here indicate the same problem here. Okay, so this distance is Y, this is our B by 2. Okay, and this is our R. So and this of course acting as a right angle triangle here. Okay, so we can write that B by 2 square is equal to R square minus Y square. So we can write B is equal to 2 times of square root of R square minus Y square. So this is our width of the strip. Now so we can calculate the dA. Okay, so dA is equal to B, that is 2 root R square minus Y square. Okay, into dy. Okay, now if I want to calculate the first moment of area, that is AY bar, so I can write it as integration of y dA. Okay, now here we can write it as integration of, and y is our y here remains same, the dA become 2 root of R square minus Y square times of dy. Okay, and this y limit is from Y to your radius R. Okay, of course now this area we generally use now. Okay, so this is from your Y to R maximum. Okay, now if I want to integrate this, so I will obtain AY bar, and AY bar. So of course you might be thinking that why didn't I use A and Y bar separately here. Okay, so we can say that our A area is varying. Okay, varying in this circle. Okay, also our Y bar will be varying hence. So since both are varying, I have combined both to calculate our first moment of area. Okay, and if we want to integrate this, so integrating this, let's say if I substitute y square is equal to, so if I substitute y square is equal to, let's say z. Okay, so I can write 2y dy is equal to dz. Okay, so I can write here AY bar is equal to integration of, now 2y dy I can write it z, so R square minus z. Okay, into dz. Okay, now if we talk about limits, so at y is equal to y, our z will become at y is equal to y, our z will become root or we can write z is equal to y square. Okay, and at y is equal to r, I can write or I can like write this completely. R square minus y square is equal to, if I write, is equal to z. So from here let me write one more. So this will become root z times of dz. Okay, and of course negative term will be here. Okay, now at y is equal to y, if I talk about it, y is equal to y, z will become r square minus y square, but at y is equal to r, our z will become 0. Okay, so now our integration will be from r square minus y square to 0. Okay, so if I integrate this, so I will obtain like z की power half, I will obtain z की power 3/2 divided by 3/2, and of course will be from r square minus y square to 0. So I can write ay bar is equal to, so if I substitute the values, I will get 2/3 times of r square minus y square times of की power, sorry, r square minus y square की power 3/2. Okay, so this is our value of ay bar, and if we use this value here, so I will obtain the value of tau is equal to, s will remain same, ay bar has become 2/3 times of r square minus y square times of the power 3/2 divided by our inertia, moment of inertia for square is pi d की power 4/64, and if we convert it in terms of radius, so it will become pi r की power 4/4. Okay, into b. Our b I have calculated here is 2 times of square root of r square minus y square. Okay, so from here I obtain tau is equal to 4s by 3 pi, 4s by 3 pi, of course r की power 4 will remain here, times of r square minus y square. Okay, so here also this relation is parabolic, and if we see here, then at y is equal to 0, sorry, at y is equal to plus minus r, value of tau will be 0. Okay, and if I like use dt by dy, d tau by dy is equal to, so is equal to 0. So from here I will obtain our value of y is equal to 0. It means that tau max at y is equal to 0. Okay, so I can draw the curve here, so it will be something similar to as we have drawn in case of your rectangular or triangular. The same type of curve will be obtained here. The maximum value reaches at neutral axis, and again the value decreases. Okay, tau max. Okay, now again if I want to calculate the value of tau max, so I will obtain it as 4/3 times of tau average, and of course you know that tau average is given by s upon pi r square. Okay, now so we have calculated here up to here. We can also calculate the location where tau is equal to tau average. Okay, now if we substitute the value of both values, so we will obtain from here that at y dash is equal to plus minus r/2. Okay, plus minus r/2, our tau is equal to tau average. Now if I talk about the fourth example, the fourth example we generally use is shear stress distribution in I section. Okay, so in case of our I section we will use this Now, so let's say that this is our I beam, I section, okay, and the dimension is as follows. So this dimension is mentioned used by capital B, okay, and this is our small b, okay, and this depth is mentioned using small d, okay, and this depth is mentioned using your capital D, okay, and of course as we know that this is our neutral axis, okay. So we will draw the stress distribution for this section, and for that we will as usual consider a section at the distance y, okay. So let's say this is our distance y, or let me draw it somewhere outside. So let's say that this is our section at a distance y. So if it at this section I want to calculate the value of your shear stress, this is fiber EF, okay. Now we have to consider this complete area here. I hope you understood this point, okay. Now to calculate this, so let's say that this is our centroid for this section, okay, and the centroid will be at a distance of y bar, okay. I hope you understood till this point. Now according to this value of y, so this y might be in our flange portion or might be in our web portion, okay. So I don't know if previously if I mentioned it or not. So this section is called flange, and this section is called web, okay, and this section of course again flange, okay. Now if I want to calculate the shear stress in let's say for calculations for or shear stress in flange, okay. So if I want to calculate the shear stress in flange, so I can of course start using same equation, that is SAY bar upon IB. This is the standard equation, and if it is, let's say that in flange, in this y is here, okay, let's say this is our relation for position for y. Let's say this is our position for y. If this is our position for y, so what will happen? What do you think? So if you think carefully about this, so our of course shear stress will be the same. Now if we talk about the area of the flange above the gap y can be given by width into depth. Width will be b and depth will become, that is d by 2 minus y, okay. So you understood till this point, okay. A into y bar. Now if I talk about y bar, so as I have done in case of rectangular section only, so this will be average of this distance, that is d by 2 minus y by plus y by 2, okay. Now if I talk about your moment of inertia, so let's write in terms of I only. I will show you how to calculate the moment of inertia for an I section, okay, or of any section. So I will calculate the I value here into B. Now B here is capital B, okay. This is the width, okay. So if I solve this, so I will obtain tau is equal to S upon 2I times of d square by 4 minus y square. So this is our shear stress distribution in flange, and this of course is parabolic, okay. Now from here we can also say that at y is equal to plus minus d by 2, the value of tau is equal to 0. Okay, so value of tau here and here will be 0. We know this. Okay, now so we have, so similar variation will be in this also, we know that. Okay, we won't be moving into that section. Now if I want to calculate the shear stress in, let's say, flange, if we talk about I have already discussed about flange. If I talk about web, okay, so if this act in your web, so we see that in case of web, if we consider this section, so area and y bar both will be varying according to distance y. So I will consider here calculate the value of ay bar combined. Okay, so I can write ay bar is equal to a1 y1 bar plus a2 y2 bar. Now this section here, okay, or let me write it with another color. Let's use this white color. Okay, so let's say this is our section 1, this is our section 2. Okay, and this is our partition here. Okay, so we will use terminology 1 for flange and 2 for web. Okay, so a1 area of flange into y1, that is your distance, centroid distance for one flange. Okay, so similarly we can write that ay bar is equal to area of flange is b into d by 2 minus d by 2. Okay, into, so this is our a1. Okay, into, if I talk about y1, so y1 can be written as d by 2 plus d by 2 by 2. This is our average of this, and this will be our y1. Plus if I talk about a2, let me write it here only, plus a2, so a2 will be width is b. Okay, and depth will be d by 2, or yes, d by 2 minus y. Okay, and similarly y2 bar will be d by 2 plus y divided by 2. Now if I solve this, so I will obtain value of ay bar is equal to, is given by b by 8 times of d square minus d square. Okay, plus b by 2 times of d square by 4 minus y square. So this is our ay bar. Now if I substitute this in our tau equation, okay, so we will obtain, if we solve this, so we will obtain the value as s upon 8I b by b times of d square minus d square plus s by 2I times of d2 by 4 minus y2. Okay, now from here you can see that this first term will be constant, because all the values here are constant, and the variation will be due to second term only. Okay, and this variation is also your parabolic variation. Okay, I hope you understood till here. Okay, now if I want to calculate we have calculated the value in the flange in the web. Okay, now at this intersection, at point above in the flange and in point of the web, there will be of course some discrepancy in the value, not like some those discrepancy, like there will be some difference in the value of the stress obtained. Okay, and we can obtain that value of stress using the equation. Let's say at if I say at y is equal to d by 2, okay, at y is equal to d by 2, we have obtained. Now if I talk about this for this in flange, first is in flange and second is in web. Okay, so in case of flange we will consider this equation, of course. Okay, and from here we will obtain tau at d by 2, tau at d by 2, okay, will be s upon 8i times of d square minus d square. And for web we will use this equation here, and from here at tau is d.2 d by 2 we will obtain. So if we use like y is equal to d by 2, this one will become 0. So we will obtain s upon 8i times of capital B by small b times of d2 minus d2. Okay, so this is our relation. Okay, so from here we can say that since this value is greater than 1, so like in the web, tau at d by 2 value is greater than that of in flange. Okay, and for here we can also like do one more thing, like we can calculate the tau maximum. To calculate tau maximum we can use d tau by dy is equal to 0, and on solving this we will obtain that at y is equal to 0 our tau is equal to maximum. Y is equal to 0, tau maximum will exist. Okay, and the value of tau max, if I want to calculate, I will simply use this equation only. Okay, so from here I will obtain s upon 8i times of b by b times of d square minus d square plus s upon 8i times of d square. Of course you don't have to like remember these equations. Okay, you can directly solve it in the examination. Okay, here we are just practicing it. Okay, so here we have seen all, like I would like to draw the stress distribution here. So to draw the stress distribution, we know that here it is parabolic. We have calculated the value of tau at d by 2, and that in flange and web. So it is something like this. So this is this value, and of course it increases to b by b times. Okay, now here the parabolic again, and it comes back to here only. Okay, let me draw it in some sophisticated manner like this. Okay, so this is our tau maximum. Okay, and this of course here it again decreases to this point, and it is like this. Okay, so I hope you understood till this point. So this is our shear distribution for I section. Okay, okay, now like I mentioned earlier, how to calculate the value of I. We have written all in terms of I. So if I want to calculate the value of I, so I have mentioned that I can be calculated by, let's consider this diagram. So we can see that there are three parts. This is flange, two flanges, and one web. We can like add the moment of inertia or all these three parts about this neutral axis, or we can like consider this big section, big rectangular section minus two smaller rectangular sections. Okay, or if even if we shift web to this corner, so it won't be making much difference. Okay, so let me write it value of I here. So the inertia area, moment of inertia of your bigger rectangle, that is b dq by 12 minus of the two smaller ones. So for two smaller one, I can write in terms of one bigger one, like I can combine two smaller ones as like both are parallel na. So I will like like take the width as capital B minus small b. Okay, so capital B minus small b, this is our width, and depth is our small d by 12. Okay, so this is our moment of inertia about neutral axis for I section. Okay, so in similar way we can draw or calculate the shear stress values and draw the shear distribution for different sections. Okay, now if we talk about composite sections, so if I talk about shear stress in composite section, composite sections. Okay, so shear stress in composite section, if we talk about this, so for this we have our relation is written by tau is equal to s times of ay bar of equivalent, okay, upon moment of inertia of equivalent into b of equivalent. Okay, so your first purpose in calculation of shear stress for composite bar is to find the equivalent section. Okay, only by finding the equivalent section can we calculate the shear stress distribution in case of your composite sections. So here I have shown the stress distribution for some various type of figures. Okay, so let's say that this is our cross. In case of cross, like here we can see that our width, like here is small b and here is our capital V. Okay, so it is exactly opposite to your that what happens in case of your I section. In case of your I section, I in flange, I mean shear stress in the flange, not opposite, is actually similar basically. Okay, opposite in terms of your geometry. Okay, but similar in terms of your flange and web. So this is the flange and this is your web, and again the similar type of things happen here. Now in case of T section also similar things happen. Okay, now here this is our T maximum somewhere here, this is our tau max. Here also that this is our tau max. Okay, now in case of your hollow circle also like this, here we will get our tau max. Okay, in case of your L section it is similar to that of in case of your shear your T section. In T section, let's like if we move this area to this side, so this will also become L. Okay, so here also like the maximum will lie somewhere here, tau max will be somewhere here. Okay, now in case of a composite section, as I mentioned, we will convert it into your equivalent section. Okay, and let's say that if E1 is greater than E2, so this will be something like this I section, and its distribution in both are equal, same. Okay, this is tau max, so this is here is tau max. Okay, so I hope you understood this chapter, the theory of this chapter. In like next session we will solve some questions. Okay, and after that we will start our next chapter. So thank you for this lecture.